In this lab 3, we'll do some data flow modeling. We'll discuss some concept about the data flow modeling and construct of the Verilog languages that will be used in initial projects. And in fact, not only the initial projects, all the projects needs to carry use these concepts. So this is pretty important. We'll have like two part of the data flow modeling. This is part one, where we just go through the syntax, and then in second part, which is lab 4, we'll be talking more about a concrete example, experiment code. We'll do some demonstration and explanation of the code live on ModelSim. So this part is theory part only. Please go through the Verilog book for more details about the syntaxes and formats in the Verilog and what is the underlying concept. In this part, in the video, this video will just touch base on whatever is important and needed to continue your experiment and project. So there are these operators like any other languages. Verilog has operators. Like any other languages, it has like unary, binary, and ternary operator. Unary is like it involves one variable at the right hand side expression, like a equals not b. Binary is it involves two operands for the operation. That is binary. Example like here, a equals b, logical, and c. And ternary is involved like three operand in the expression. Like if you at least I know in the C language it has this construct. It means that test a b, and if b evaluation becomes true, then assign the value of c to a, else assign the value d to the variable a. The pseudocode of this like if b, a equals c, else equals d. So this is ternary operation. Now there are number specification. This is special from many other traditional languages, since Verilog needs to deal with very low level number formatting, which usually is hexadecimal, can be binary or octal or decimal. So it supports all these four formats of any number, and then it is good to actually specify this notation with the size, base format, and a number, and there is a little tick between the size and the base format. If we don't specify size and base format, any number we write, it assumes to be, at least try to assume it is an decimal number. That means if you define something 10a, which is a perfect hexadecimal number, it will not try to infer that as a hex by default. It will try to infer that as a decimal, and most probably give you a compilation error right there. But it is always a good practice to actually specify the size and the base format, even if we are defining a decimal number there. So some example like 6 tick h10, this means my number is 6-bit number. In hexadecimal format it is 10, so 10 base 16 with a, so by default Verilog simulator assumes a 32-bit number, but we can actually specify depending on what is our bus and address size, stuff like that. We can actually define precisely how many bits the number needs to have. For example, here is a 6 tick O, means 6 begin 6-bit number in octal. 6-bit 10 means it is 6-bit number in binary. So practically the internal representation will become 000010. so 6-bit. All the left hand side bits at 0, only 10 at the rightmost side is a number we are looking for. Similarly, on the decimal side, it is 6 tick 10. It is a 10 in the decimal. Now the unsigned number, as I mentioned, that if we don't specify anything like size or the base format, it assumes 32-bit decimal. If we don't specify size in the hex, it is bits and also octal, so on and so forth. For binary, it's 32-bit binary. Now there are 4 value types in Verilog: 0, 1, X, and Z. Okay, so this is kind of on four types of I would say it's a logic value we are talking of here. This is like each of the Verilog signals are ultimately as one bit logic signal. You can think of in that way. See, when I specify a number like decimal number, let's say 2356, that internally that is basically 32 bits of wires or 32 bits of lines which have a specific 0 or 1 value. So logic 0, logic 1. So fundamentally, Verilog simulator value types are just 1-bit representation, and it can be either 0, which is logic low or false, 1, which is logic high or true, X, which is unknown, and Z is a high impedance. So Z is a little bit more geared towards the electrical domain. You can imagine if an wire is floating, not connected to anything else, no logic being driven, that means the wire is completely electrically isolation state. That value is denoted with a Z. Okay, and X is unknown. Like at certain point of time, Verilog simulator doesn't know what is the value on that line or on the wire or on the variable, 1-bit variable. What is the value, doesn't know. So that is X value. And Z is, it's a state which is electrically isolation state, which doesn't have any logic like 0 or 1, but it is not unknown. It is high impedance value. Now data types, we have nets, as I have mentioned in earlier labs slides, that nets are declared as a wire. It's kind of connection between hardware element, just like a real circuit. You, like in a real circuit board, you can join one port with another IC pin or something like that with using a wire. So it is just like that. Like it is connecting between two hardware element, like in wire, and so we declared that as a wire. It can be a, like any name you do, and by this, if you don't have any parentheses like square, open square, closing square, and with some dimension value in it, it is treated as a one bit wire. And register, on the other hand, represent the unsigned data storage element in the simulator. It is not the same as the hardware register that we'll be learning later in the digital design section. Just keep that in mind. Like when you do a reg A, it is not, we're talking about a like sequential circuit element register, but it is just an storage, unsigned storage element simulator. And again, like the where, if I just do declare and register variable without any dimension, default it is 1 bit. Okay, like compared to like Java, for example, if I define something like integer a, default it is an 32-bit storage, but here reg a means 1-bit storage, where a means 1-bit representation of the signal. Now vectors is kind of to define, it's more or less similar to the array, but beware, there is an separate array type as well. We'll see that. Vector is kind of trying to define or group bunch of signal together within one name, and it's referred each of the element inside the group by index number, like integer index number. For example, like var square brace 7 colon 0 bus, which is practically giving you the 8-bit bus, and each of the bit element we can actually refer as bus open square brace 0 close square brace, or bus open square brace 5 close square brace. So this is kind of a way to group multiple bits together within one name. Similarly, for the register also, we can do like a 32-bit register storage, like 31 versus 0 colon 0. That means I have 32-bit storage index from 0 to 31, and each of the bit I can, in that group, I can access by the index number. Unlike any other programming, like any other programming, there are integer and real numbers also. These are mostly for the test program implementation. These are not directly related to the hardware, but it like comparison of result and all this programming part of a test bench that uses this kind of data type, like integer, real is basically floating point number, so on and so forth. Now arrays is Verilog supports arrays, but it has to be a single dimension array. It doesn't support multi-dimension. Okay, so what does it mean? Like, let's say it's an integer counter, and integer counter of 0 to 7, which means it's an 8-element counter of integer, and you know the integer is 32-bit. So it is just like an array in the normal programming scenario. So it is an array of 8 element. Okay. Now, if I specify like this, reg 70 mem 02048, which means I am defining an array of 2 kilo storage, which each of them is 8-bit bus, 8-bit groups. So it's basically it's an array of 2 kilo of 8-bit register. As you can see, like I chose the variable name as mem. In fact, these type of notations are used to define memory inside the Verilog. Like, you know, the memories are have certain number each. Memory is a storage of multiple words, and each word can be of multiple bits. So here we are declaring that, okay, my word length is 8-bit, so I have register storage of 8-bit, and I have 2k such 8-bit register. Okay, so this is array, this is vector. Array and vector. This is a little tricky concept in the Verilog. Just get used to this convention, then we should be fine with that. Okay. Now there are one rule we need to always remember while we are connecting different different logic element in the Verilog, which is like which port can be connected to which type of element in the simulator. For example, if this is a block, top level, it's a block, and then it has like 3 different ports, like input port, output port, and input output port. Then the rule is that an in-out port can only be connected with a net or wire, either inside or outside. Okay, it has to be wire. And output port, it on the outside of the block, it has to be connected on a net or where. Inside it can be a net or register. Okay, so either it has the ultimately through the hierarchy somewhere down below, it has to one single where has to be driven by a register storage within the simulator, but it can be in the like higher hierarchies, it can be a net to net connection. So output can be connected out has to connected outside with a net, but from inside we can either connect a net or register. For the input port, inside it has to be a net connected to a net. It cannot be input port cannot be connected to a register, but at the outside of the block it has to either come from a it can either come from a register or a net. Okay, so right now it may not be very clear to you that all these rules, but once you start doing coding in very long, we'll see these rules. Like if we don't follow this rule, compiler will simply give this some error. For example, like let's say there is an input port. Okay, let's say there is an in-out port and we try to connect a register with the in-out port from outside or inside, it will give a compilation error. Okay, as an output port, if we want to go and try to connect a register there, it will complain about that. Okay, so that's the basic thing. And if for the input, similarly for the example, like if I want to connect and register from inside of the block to the port, top level port of which is input type, it will give a problem. So we need to very clear about this rule. And if you see such message about the incompatible ports, port connection or something like that, so that means you probably inside the code you violate one of this rule. Okay, so in the next section we'll see more details on we'll use this construct and these ideas of different data types to build more concrete blocks, and we'll discuss more on this data flow modeling in the next section of the lecture.